Why the F-47's new shape-shifting engine makes it untouchable. For decades, designing a fighter jet has been a game of brutal compromises. Do you build an engine for blistering Mach to speed that burns fuel so fast it can barely reach the fight? Or do you design it for long-range, efficient cruising, knowing it won't have the raw power to dominate a dogfight? This trade-off has defined the limits of air power. But what if that compromise is now over? America's answer, a technology demonstrator that has been flying in secret for years, is finally moving into production. In March 2025, Boeing won the contract to build the Air Force's next-generation air dominance, or NGAD, platform, which has been designated the F-47, and its revolutionary, shape-shifting engine is what makes it truly untouchable. Here's how. To get why the F-47's engine is such a monumental leap, you first have to understand the basic physics that have boxed in every fighter jet until now. At its heart, a jet engine is just a controlled explosion. It sucks in air, compresses it, adds fuel, ignites the mix, and blasts hot gas out the back to create thrust. The compromise is all about how much air bypasses the engine's core. Think of it like this: a pure turbojet, like on early supersonic fighters, shoves almost all the air through the hot, violent core. This creates a super fast exhaust stream, perfect for high speeds, but it's incredibly loud and horribly inefficient. It's a sprinter who's out of breath after 100 yards. On the other end is a high bypass turbofan. Like the massive engines on an airliner, they push a huge amount of air around the core. This bypassed air is slower, but it creates a ton of thrust very efficiently. It's a marathon runner who can go for miles at a steady pace but can't suddenly break into a sprint. For the last 50 years, military engines have been stuck in the middle, low bypass turbofans. The kind you'll find on an F-15 or F-22 are a blend of both concepts. They're pretty good at everything, but not exceptional at any one thing. Their breathing pattern is locked in from the day they're built. This has created a massive headache for military planners, especially in the vast Pacific, the tyranny of distance. A fighter taking off has to choose: carry more fuel for range, making it heavy and less agile, or carry more weapons, which limits how far it can go. Even 5th-gen marvels like the F-22 Raptor, with a combat radius of around 470,600 miles, are bound by this law. They are utterly dependent on huge, vulnerable aerial refueling tankers to get anywhere near a fight, and in a future conflict, those tankers are target number one. A new solution was needed, not just an improvement, but a complete paradigm shift. The solution comes from a revolutionary concept developed under programs like the Adaptive Engine Transition Program, or AETP. The result is an adaptive cycle engine, the heart of the F-47. Competing designs, the XO-102 from GE Aerospace and the XO-103 from Pratt & Whitney, are being developed under the Next Generation Adaptive Propulsion NGAP program to power the new fighter. So what makes it shape-shifting? Unlike any engine before, it doesn't have a fixed bypass ratio. Instead, it has a game-changing feature: a third stream of airflow. This outer duct can be opened or closed in real time, letting the engine literally reconfigure itself in mid-flight. It can change the way it breathes. Imagine the F-47 on a long-range patrol. The pilot needs maximum endurance. The engine opens that third stream, letting a huge amount of cold air flow around the core. It starts behaving like a super-efficient airliner engine. AETP's goal was a staggering 25% improvement in fuel efficiency, which is projected to translate into a 30% increase in the F-47's operational range. This allows the F-47 to fly deeper into enemy airspace, loiter longer, and get home without needing a tanker. But then, an enemy jet appears. The mission instantly changes from a marathon to a sprint. The engine's controls react, closing the third stream and forcing all the air into the core. Just like a classic turbojet, the engine transforms into a high-performance beast, optimized for raw power. Program goals call for a thrust increase of 10-20 over today's best engines. This ability to switch between a high-efficiency cruise and a high-power combat mode is the engine's magic trick. It's not just two engines in one. It's an infinite spectrum of performance. The F-47 no longer has to choose between being a sprinter or a marathon runner. It can be both. Simply opening and closing an airstream sounds easy, but making it work required a revolution in materials, manufacturing, and digital design. The companies competing to build this engine, GE and Pratt & Whitney, have been running thousands of digital simulations to perfect the complex mechanics before forging a single piece of metal. At the center of this revolution are new, exotic materials called ceramic matrix composites, or CMCs. Traditional engine hot sections are made from nickel-based superalloys, which are strong but heavy and have a temperature ceiling. CMCs, made of ceramic fibers in a ceramic matrix, can withstand temperatures hundreds of degrees hotter than even the most advanced alloys. The hotter an engine runs, the more power and efficiency it generates. Plus, CMCs are about one-third the weight of their metal counterparts. By swapping heavy metal parts in the turbine and combustor for CMCs, engineers can build an engine that's not only more powerful and efficient but also lighter. The manufacturing itself is also futuristic. Both developers are using additive manufacturing or 3D printing to create impossibly complex components. Intricate cooling channels can be printed directly inside turbine blades, and parts that used to be dozens of separate pieces can now be printed as a single, stronger, lighter component. This doesn't just improve performance, it radically speeds up manufacturing. These two technologies, CMCs and 3D printing, are what make the adaptive cycle possible. They allow for the creation of variable components that can withstand the intense heat and pressure as the engine shifts modes. After completing their detailed design reviews in early 2025, both GE and Pratt & Whitney are moving into building and testing prototype hardware for the NGAP program. The result is a system that doesn't just produce thrust. It intelligently manages air, heat, and power on a level never seen before. So what does this revolutionary engine actually mean for the F-47 in a real fight? It means the rules of air combat are about to be rewritten. First, range. The projected 30% increase in operational range is a strategic game changer. The F-47 is expected to have a combat radius of over 1,000 nautical miles. This isn't just an improvement, it's a capability that redraws the strategic map. It means the F-47 can launch from bases far from the front lines, penetrate deep into enemy airspace, and return without a vulnerable tanker. It can stay on station for far longer, providing cover and awareness for other forces. Next is raw power. The adaptive engine allows the F-47 to supercruise flying at sustained supersonic speeds, likely over Mach 1.5, without using its fuel-guzzling afterburner. An afterburner is just raw fuel being dumped into the hot exhaust for a massive, but temporary, power burst that can drain a fighter's tanks in minutes. By supercruising, the F-47 maintains a high-energy state throughout an engagement. It can close with enemies faster, dictate the terms of the fight, and escape threats without a crippling fuel penalty. In a dogfight, energy is life, and the F-47's engine gives it an advantage no fixed cycle engine can match. As of late 2025, the F-47 program is moving from secret prototypes into early manufacturing, with Boeing already starting to build the first airframe, while some timelines are ambitious, with hopes for a first flight around 2028. The immense complexity of these systems means flight tests are more likely to begin closer to 2029 or 2030, with the jet becoming operational in the 2030s. But what if the engine's greatest trick isn't about speed or range? The adaptive engine's most profound contribution to the F-47's invincibility might be how it handles heat and power. This is where the third stream of air plays its most critical, game-changing role. That third stream isn't just for bypassing the core. It's a massive river of cool air flowing through the engine. Every piece of electronics on a stealth fighter generates a ton of heat, and heat is a mortal enemy. An aircraft's hot skin and engine exhaust create a huge infrared signature for heat-seeking missiles to track. The F-47's adaptive engine uses that cool third airstream as a giant heat sink. It can be ducted throughout the airframe to cool the radar, mission computers, and even the jet skin. This air is then mixed with the hot core exhaust before it leaves the nozzle, dramatically lowering the F-47's overall infrared signature. It becomes exceptionally difficult for enemy sensors to track, making it thermally stealthy. In an age of increasingly sophisticated infrared tracking systems, this is a revolutionary leap in survivability. Even more significant is what this cooling enables: power for the future. The next generation of air warfare will be defined by power-hungry systems, most notably directed energy weapons, or DEWs. We're talking about high-powered lasers that can blind sensors or destroy drones at the speed of light. These weapons could make traditional missile defense obsolete, but they need a colossal amount of electrical power and generate just as much waste heat. The adaptive cycle engine is being designed from the ground up to be a flying power station. It will provide the immense electricity and, crucially, the thermal management needed to make directed energy weapons a practical reality on a fighter jet. This capability to generate and cool megawatt-class systems is what truly puts the F-47 in a class of its own. The F-47 was designed as the centerpiece of a new family of systems for the NGAD initiative, but at its core, it's the revolutionary adaptive cycle engine that gives it the performance, endurance, and power to be untouchable. By eliminating the old compromise between speed and efficiency, it provides unmatched performance. By mastering thermal management, it achieves a new level of stealth. And by unlocking the potential for directed energy weapons, it opens the door to a new era of air combat. But what do you think? Is the adaptive engine the key to the next generation of air dominance, or will other systems like AI and drone command be more decisive? Let us know in the comments.